Hello everyone. In this video tutorial, I'll demonstrate the phase formation prediction during remelting and oxidation of zinc galvanized steel using FactSage software. In industries, the manganese and chromium containing steels are galvanized by zinc, which is kept in atmospheric condition. Now, during reheating of uh, this galvanized steel at 900 degrees centigrade, this reheating temperature is way above the melting point of zinc, which is around 420 degrees centigrade. So, zinc liquefies at this high temperature, and while zinc liquefies, the interface between solid steel and liquid zinc, there is interfacial reaction, and in the interface of liquid zinc and the atmospheric air, there is oxidation reaction. So we can predict the phases which forms in from uh, this atmospheric from the oxygen which comes from the atmospheric air, which reacts with the liquefied zinc bath, and that can be done by controlling the partial pressure of uh, oxygen at different layers of oxides. But the partial pressure is not linearly decreasing with depth of the oxide layer, as you can see. So the type of calculation shows quantitative oxidation behavior only. At first, we will do the interface reaction between a liquid and steel, which will simulate in FactSage. In order to do that, first we will open FactSage. In FactSage, we will open Equilib module. To open Equilib module, we will go to the Equilib button and then left mouse button click on this Equilib button. After the Equilib dialog box opens, we have to first select the databases. So to select the database, we have to go to data search option and click left mouse button. Here we will select the FT-Lite database only, because FT-Lite database contains reasonable zinc bath data for zinc galvanizing calculation. So this FT-Lite database is chosen uh, instead of the FSTIL database. So after selecting the FT-Lite database, we will click on OK. Now we have to enter the reactant species. In order to enter the reactant species, we have to go to this plus sign, which is add new reactant button, and click left mouse button in here. So in this case, first we have to add zinc, then our steel composition. So in our steel, we have iron, we have chromium and manganese. So the total amount of zinc we are taking is 100 gram of zinc, then iron is 99.5, and then the alloying elements chromium to be 0.5 weight percentage and 1 weight percentage of manganese. So after we put all our reactants and its amount, we have to go to the next, the menu window. In the menu window, first we will select all the solution phases. To select all the solution phases at once, we will go to select button and click left mouse button and select all solution. Then we will also select all the pure solids. To select all the pure solids, we have to go to the white box near the pure solids and click left mouse button on there. So after clicking the left mouse button, the pure solids, all pure solids are selected. To see which solids we have selected, we'll go to the pure solids and click right mouse button on it. Here all the green areas shows the pure solids we have selected for our calculation. After selecting all the pure solids, we will click on OK. Then we will put the temperature at which we want to do our calculation. For this case, we will put 900 degrees centigrade. So after putting all the values of the variables, we will do the calculation in FactSage. To do that, we'll click left mouse button on calculate button. In this window, FactSage calculated the equilibrium calculation and it shows two different phases at the interface. One is liquid, which is zinc rich liquid. This is a reaction product of the interface reaction where there is a zinc rich liquid and then there is a BCC solid phase. Now if we see the schematic diagram, here we can see that this is the original steel which is solid, and this is the reaction zone where liquid reaction products are there, so which is zinc rich liquid which corresponds to this liquid phase, and then there is reaction product which corresponds to the solid phase. Now we will use this liquid or zinc rich liquid. This zinc rich liquid will be used for future calculations, for oxidation calculations, and we need this zinc rich liquid for oxidation reaction as I have told, and then we'll save it as stream file. In order to save this liquid phase, which is written as liquid -1 as a stream file, we have to go to output and left mouse click on this output option and then click on stream file and then save stream file, and this is a solution, so we'll go to save solution and this FT light liquid -1, because this corresponds to the actual liquid phase, so we'll select this one. So we have to give a name, so we'll give the name zinc liquid. The name again, zinc liquid. The next calculation is oxidation reaction of liquid zinc. So we will use the stream of liquid zinc which we saved from previous calculation and use it for oxidation reaction. To do that, we have to go to the equilibrium module again. Here I have opened the equilibrium module. Here we'll import the stream. In order to import the stream, we have to go to edit option, left mouse click on this option, then mixture and streams, and then go to import a stream. Here I have saved liquid zinc liquid stream. Left mouse click on this option and this stream file is imported. And also we want to add oxygen because oxygen will react with the liquid zinc. So we'll input oxygen. Now we will not specify the amount of oxygen here, so we'll put 0 because we will uh, incorporate the partial pressure, fixed partial pressures for oxygen in the next window. So we don't have to specify the amount in this boxes. Then we'll go to next. Also, as we have incorporated the pure oxygen in here, which is gas phase, we have to select the proper database for it too. To do that, we have to go back to the reactants window and then go to data search, where we will add the gas and pure compound and element database. To do that, we'll go to the data search and click left mouse button and select the FactPS database. And then after selection, we have taken all the required databases, so click OK. After this, we will go to the next window and we see the gas is there to select. To select the proper gases, we don't want to take any other gases, only oxygen. We'll go and right click on this gas text with our right mouse button. Here there are a lot of species of gases, but we want to select the oxygen for calculation. So we'll click on that with right mouse click, and then first we have to select it. So we'll select it with left mouse click, and then also click it with right mouse button, and then select the activity of the oxygen gas. So for this case, we'll take activity in log scale, which is in gaseous phase of activity is a partial pressure. So we'll start from minus 30 to 0 with interval of 0.5, which give us the whole range of oxygen partial pressure. After selecting proper activity data, there will be A shown here. So A denotes fixed activity as the pop-up window shows, and then we'll click OK. After doing this, we will do the calculation again at 900 degrees centigrade. So all our input data is given. So we will click on calculate button. Here in the result window, Faxes calculated the products at different activity of oxygen, and we want to plot the amount of every phases with different partial pressure of oxygen using figure module. So to plot the data, we'll go to output and left mouse click on it, and then go to plot and then plot results. Here we have to select the axis. So in this case, we want to see what are the products, the amount of products which are formed at different partial pressures of oxygen. So we will keep the partial pressures of oxygen in log scale in our y-axis, in our x-axis, and the products as gram in our y-axis. To, to do that, we'll go to axis, and at y-axis we'll take gram. To to take what uh, item we want to put in our y-axis, we have to go to y variable and left mouse click on that, and then we'll select gram, and our x variable we want to put the partial pressures of oxygen in log scale. So we'll click on x variable and select activity also in log scale. So we want to vary our activity, in this case from -30 to 0 with every 5 degree 5 uh, to the 5 atm oxygen partial pressure interval. So it take at every 5 as it is in log scale. So we click, after giving all the input for our axis, we click on OK. Then we have to select the phases. To select the phases which will form in the condition which we have given, we'll go to select and put left mouse click. It will open all the phases which we have selected. So in between all the phases, we want to select all the phases which are formed in this calculation. So we'll go to select and put left mouse button click there and select all the stable phases. Also, we want to put that which activity we should put in our x-axis. So it is the in the x-axis what is the activity, which species we want to put, and we want to specify the number. These are the number of the species. So we want to put the partial pressure of oxygen in our x-axis. So we will put the number 1, and after that we will click OK. So all our input data are given here. So we will click on plot with left mouse button. So here in the diagram which is plotted by FactSage in the figure module, we can see that at different partial pressure of oxygen, what type of oxide phases and the phases which are formed. This is liquid zinc, and then above this partial pressure there is oxide phases which are forming, and also there is a very low amount of this oxide phases are forming. To see what is the amount, we have to decrease the range of y-axis. So to do that, we have to go to this gram text and left mouse button double click on this gram. This will open this dialog box where we can tweak the data of x and y axis using this frame and axis dialog box. So here we will decrease the range of our y-axis from 0 to 5 gram, and we'll put levels and increment to be 1 gram. Then after putting all the data, we'll click on OK. So here we see all the uh, phases which are very low amount which are formed. which can be seen very easily, visualized very easily by changing the y-axis range. Now, if we put all those both of the diagrams side by side, we can easily make a schematic diagram of all the oxide phases which are formed. As you can see that this ZNO and ZNF304 forms the zincite and spinel phase, which is zinc ZNO rich zincite phase, and then other amino rich monoxide phase and ZnCr2O4. All these phases which you can see from the calculation which are formed. And but there is one thing is that it is very hard from this thermodynamic calculations, as I've shown, it is very hard to expect the thickness of each layer.